All right, common collections part 2, I believe. Let me open that up. And we're talking about strings, storing UTF-8 encoded text with strings. And looks like there's a lot of dialogue before we get into editor stuff. So let me just make this big. Let's go. We talked about strings in chapter 4, but we'll look at them in more depth now. New Rust people commonly get stuck on strings for a combination of 3 reasons. Rust's propensity for exposing possible errors, strings being a more complicated data structure than many programmers give them credit for, and UTF-8. These factors combine in a way that can seem difficult when you're coming from another programming language or other programming languages. It's useful to discuss strings in the context of collections because strings are implemented as a collection of bytes, plus some methods to provide useful functionality when those bytes are interpreted as text. In this section, we'll talk about the operations on string that every collection type has, such as creating, updating, and reading. We'll also discuss the ways in which string is different from other collections, namely, how indexing into a string is complicated by the differences between how people and computers interpret string data. What is a string? We'll first define what we mean by the term string. Rust has only one string type in the core language, which is the string slice stir that is usually seen in its borrowed form with the ampersand string. In chapter 4, we talked about string slices, which are references to some UTF-8 encoded string data stored elsewhere. String literals, for example, are stored in the binary output of the program and are therefore string slices. The string type, which is provided by Rust's standard library rather than coded into the core language, is a growable, mutable, owned UTF-8 encoded string type. When Rust people refer to strings in Rust, they usually mean string and the string slice, ampersand string, types, and not just one of those types. Seemingly mean both of them. Although this section is largely about string, both types are used heavily in Rust standard library, and both string and string slices are UTF-8 encoded. Rust standard library also includes a number of other string types, such as OS string, OS stir, C string, and C stir. Library crates can provide even more options for storing string data. See how those names all end in string or stir? They refer to owned and borrowed variants, just like the string and stir types you've seen previously. These string types can store text in different encodings or be represented in memory in a different way. For example, we won't discuss these other string types in this chapter. See their API documentation for more about how to use them and when each is appropriate. So what they're saying here is that there are other types of strings. They map to the same borrowed variant. They refer to owned and borrowed variants of strings, just like we saw in this. Owned and borrowed, and they can map to different encodings and be represented in memory in a different way. But they're not going to be covered in this chapter because they're not relevant to this chapter. Creating a new string. Many of the same operations available with vector are available with string as well, starting with the new function to create a string as shown. So yay, we could open our editor and say let mutable s equals string new. And this is the same syntax we use with vectors, and it seems to work for strings as well. This is probably due to the fact that strings are a vector, or seemingly a vector of bytes. This line creates a new empty string called s, which we can then load data into. Often we'll have some initial data that we want to start the string with. For that, we can use the toString method, which is available on any type that implements the display trait as string literals do. Show two examples. There's two examples down here. We can start with, this has initial data in it, toString. This method also works on the literal directly. So what this example is showing is that we have our string literal let data, which is initial contents. I spelled initial wrong. Initial contents. That is a immutable string. Str, string literal, right there. If we wanted to create a string from it, I think we can do this. Equals, let's s equal data dot toString, to_string, and we can see that the type changed to string. However, if we wanted to, we could have done that directly on the string literal, which makes sense because it's just a reference to that. This would have just saved this time. Let me call this s again, equals spell it correctly this time, initial contents dot to_string. And for safe measure, let's just print this out. Because string, as they said here, implements the display trait, which means we can just print it. No debug needed. Initial contents. This code creates a string containing initial contents. We can also use the function string from to create a string from a string literal. The code and listing down out here. We've seen this method before. We've tried this string : from. We know that works. Let's just move on. Because strings are used for so many things, we can use many different generic APIs for strings, providing us with a lot of options. Some of them can seem redundant, but they all have their place. In this case, string from and toString do the same thing, so which you choose is a matter of style. Remember that strings are UTF-8 encoded, so we can include any properly encoded data in them, as seen below. And we have a lot of options here. I speak English and Chinese, so let's do this Chinese option. 你好. And put that, well, I could keep S there. Wait, I couldn't copy it? Hold on. I thought I copied it. Control copy. Control paste. Oh, I did paste it. And get rid of this line. And now we can just print 你好. Print hello. 你好. That worked. Cool. All of these are valid string values. Make sense? Updating a string. A string can grow in size and its contents can change, just like the contents of a vector, if you push more data onto it. In addition, you can conveniently use the plus operator or the format macro to concatenate string values. Okay, I want to see examples of this, especially the format. I haven't used format yet. Appending to a string with push, stir, and push. We can grow a string by using the push stir method to append a string slice as shown. Get rid of the 你好 and mess around with S. S is not mutable. Make S mutable. Mutable. This line doesn't need to be here anymore. this should work as is, unless, no unless. Now we can do s dot push. You have the push string here, and they want bar initial content, comma, space, period, space, new content. And then we should be able to print that out. Initial content, new content. All right, that's there. After these two lines, S will contain foobar, at least in their example. The push stir method takes a string slice because we don't necessarily want to take ownership of the parameter. For example, the code in listing 8-16 shows that it would be unfortunate if we weren't able to use S2 after appending its contents to S1. So let me just verify what they're saying here. It seems as though they use a string literal because they want to have a pointer to it and keep S2 valid. So if we created an S2 here, let's call this let S2 equal new content, right? And then what we push is S2. Now we want to print S, and down here let's print S2 to show that we still have access to S2, or that we can still use it. It has not been owned or deallocated. That's what I'm looking for, deallocated. And yeah, I should have put a period and a space or that. But yeah, it's there. So if we use this method, push stir, and we pass in a string literal, this does not take ownership over S2, and because it does not take ownership over S2, we still have access to it and can still use it throughout our program in this scope. Cool. If the push stir method took ownership of S2, we wouldn't be able to print its value on the last line. However, this code works as expected. The push method takes a single character as a parameter and adds it to the string. Listing 8-17 shows code that adds the letter I to a string using the push method. Oh, letter L. That's an L. So let's get rid of this because it's no longer needed for the example. Let mutable s equal string from LO, and we're missing an L. So we do s.push, and we can pass in a single character. So you can see that the type is it's char for a single character, and L. And now if we were to print S, what we should get is LOL. Laugh out loud. LOL. Cool. As a result of this code, S will contain LOL. Alright, here's what I wanted to see, the concatenation with the plus operator or the format macro. Often you want to combine two existing strings. One way is to use the plus operator, as shown in listing 8-18. So let's do that real quick. S1 equals string from hello space. Let S2 equal, capitalize that string, put some respect on it, from world, and then let S3 equal S1 plus a point of reference to S2. Interesting. And they have a note here. Note, S1 has been moved here and can no longer be used. Understood. S1 has been moved into S3, but S2 has not. And that we should be able to print S3 at least. S3, semicolon there. So hello world exists, right? And we still should have access to S2 because we used a pointer, or string literal. World is there. But we should no longer have access to S1 because that has been moved into S3. And that we had an error. Makes sense. The string S3 will contain hello world as a result of this code. The reason S1 is no longer valid after the addition and the reason we use a reference for S2 has to do with the signature of the method that gets called when we use the plus operator. Okay, so the plus operator uses the add method whose signature looks something like this. Add self and a pointed to a string, so string literal string. I see. This isn't the exact signature that's in the standard library. In the standard library, add is defined using generics. Here, we're looking at the signature of add with concrete types substituted for the generic ones, which is what happens when we call this method with string values. We'll discuss generics in chapter 10. This signature gives us the clues we need to understand the tricky bits of the plus operator. First, S2 has the ampersand, meaning that we're adding a reference of the second string to the first string because of the S parameter in the add function. So right now they're justifying having the ampersand here, and they're saying it exists because the signature of the add uses an ampersand string, string literal, so it has to be there. We can only add a string literal to a string. We can't add two string values together. But wait, the type of S2 is a pointer to string and not a pointer to stir, as specified in the second parameter to add. So why does listing 8-18 compile? So what they're pointing out here is the slight difference into what we're doing and what we're saying. What we're doing is we're creating a reference to string, capital STIRNG, and not a reference to stir, ampersand STR. And they're asking, why does this still compile? The reason we're able to use ampersand S2 in the call to add is that the compiler can coerce the ampersand string argument into ampersand stir. When we call the add method, Rust uses a deref coercion, which here turns ampersand S2 into ampersand S2, these bracket things with a dot in between. We'll discuss deref coercion in more depth in chapter 15. Because add does not take ownership of the S parameter, S2 will still be a valid string after this operation. Understood? So what they said here is that the reason why this still works is because the compiler can convert it from this to something like this at compile, well, not at compile time. Well, technically speaking, at compile time. So basically what they're saying here is that the reason why this works as it does is because the compiler can convert this to this. And they said it goes from this into something that looks like this. And that works. Okay. Second, we can see in the signature that add takes ownership of self because self does not have an ampersand. This means S1 in listing 8-18 will be moved into the add call and no longer be valid after that. So although S3 equals S1 plus ampersand S2 looks like it will copy both strings and create a new one, this statement actually takes ownership of S1, appends a copy of the content of S2, and then returns ownership of the result. In other words, it looks like it's making a lot of copies, but isn't. The implementation is more efficient than copying. If we need to concatenate multiple strings, the behavior of the plus operator gets unwieldy. And they have tic-tac-toe as an example. Oh, I can see. So we have this one. This one takes ownership of. And then we have the plus string literal, which works as is, plus ampersand, which is a pointer to string 2, string literal, which is a pointer, and then we have a pointer to string 3. That can be annoying. So instead, we can write it using the format macro. At this point, S will be tic-tac-toe with all of the pluses and string, characters. It is difficult to see what's going on. For more complicated string combinations, we can use the format macro. And here's an example of doing that. So equal from tick, let S2 equal string from tac, let S3 equal string from toe, and then they said we can define S using format macro. So let S equal format, already popped up, and now we can just do this. S1, S2, and S3. And to confirm, let's use the print line macro and pass in S3. Oh, not S3, just S, pass in S. What I am curious about is whether or not we still have access to S1, 2, and 3. So S prints out, we have tic-tac-toe. And now let's check to see if we have access to S1. Just curious. And we do. Okay, so that should imply that this format macro, did not take ownership of S1, S2, or S3, and we still have access to them within the scope. That is good to know. This code also sets S to tic-tac-toe. The format macro works in the same way as print line macro, but instead of printing the output to the screen, it returns a string with the content. The version of the code using format macro is much easier to read and doesn't take ownership of any of its parameters. Understood? Indexing into strings. I was afraid of this section because we can't really do it. I don't believe we can do it. In many other programming languages, accessing individual characters in a string by referencing them by index is a valid and common operation. However, if you try to access parts of a string using indexing syntax in Rust, you'll get an error. Consider the invalid code in listing 8-19. We have a string and we try to get the first character in the string, which is H. The code will give you the following error. And this error says the trait bound indexing is not satisfied. Okay, so we don't have a trait for indexing, so we can't do it there. And cannot be indexed by integer. Okay? But more or less, the indexing trait is not implemented, and you can't do this at all. The error and the note tell the story. Rust strings don't support indexing, but why not? To answer that question, we need to discuss how Rust stores strings in memory. Going down memory lane. Internal representation. A string is wrapped over a vector U8 I made the mistake of saying this was UTF-8 before, but I believe it's just an unsigned 8-bit integer. Let's look at some of our properly encoded UTF-8 example strings from listing 8-14. First, this one. Let length of string from hola. In this case, it should be 4. It will be 4, which means that the vector storing the string hola is 4 bytes long. Each of these letters takes 1 byte when encoded in UTF-8. But what about the following line? Note that this string begins with the capital Cyrillic letter Z, not the Arabic number 3. I'm gonna copy that because I'm curious to see what the length is. Print line. I think they say it's 12, but I like to see here. 24. Woo. Ask how long this string is. You might say 12, because I guess if we counted it says we think it's 12. Maybe it's just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12. I don't want to say character. Yeah, I think I could say characters. Characters, letters. I don't know. But there are 12 of whatever this is. Rust's answer is 24. That's the number of bytes it takes to encode this in UTF-8. Because each Unicode scalar value in the string takes 2 bytes of storage. Therefore, an index into the string's bytes will not always correlate to a valid Unicode scalar value. To demonstrate, consider this invalid Rust code. They are asking for the first byte. What is that supposed to mean? What should the value of answer be? Should it be 3? I guess it looks like a 3. It's not Z. They explain that. The first letter. When encoded in UTF-8, the first byte of Z, this thing that looks like a 3, is 208. And the second is 151. So answer should in fact be 208, but 208 is not a valid character on its own. Returning 208 is likely not what a user would want if they ask for the first letter of this string. However, that's the only data that Rust has at byte index 0. Users generally don't want the byte value returned, even if the string contains only Latin letters. If you have this thing, which is ampersand, string literal, hello, index 0, were valid code that returned the byte value, it would return 104 and not 8. To avoid returning an unexpected value and causing bugs that might not be discovered immediately, Rust doesn't compile this code at all and prevents misunderstandings early in the development process. So basically what they're saying here is that given that strings under the hood are a vector of unsigned 8-bit integers, if they were to return a specific index, they might not correlate to a valid UTF-8 character. An example they use is this language, where each character takes up 2 bytes. So if you wanted only the first byte, then you're asking for half a letter, which doesn't really make sense. And even in the case where it was ASCII, or I guess the Latin letters hello, and the first index actually corresponds to the full Unicode value, we are still returning the number, the 104 in this case, the U8 number, and not 8, which is the character. But to avoid all of that misunderstanding, they just say, you can't do this. This is going to be invalid. You cannot try to index your strings. Bytes and scalar values and grapheme clusters. I'm not sure how to say that word. Oh my. Another point about UTF-8 is that there are actually 3 relevant ways to look at strings from Rust perspective, as bytes, scalar values, and grapheme clusters. The closest thing to what we would call letters. Ooh, because you don't want to say letters because letters is implied to all languages. That makes sense. If we look at the Hindi word, that word, written in the, I don't know how to say that word, script, it is stored as a vector of U8 values that looks like this. So this is the value of this thing. I say thing, it is a word in this language. That's 18 bytes and is how computers ultimately store this data. If we look at them as Unicode scalar values, which are what Rust's char type is, those bytes look like this. And they separated them each into their own little character, plus this thing at the end. I guess that's there. Is it? I don't know. I don't know how to write that. There are 6 char values here, but the 4th and 6th are not letters. They are diacritics that don't make sense on their own. Finally, if we look at them as grapheme clusters, we get what a person would call the 4 letters that make up the Hindi word. This thing. Okay, understood. So that corresponds to this, that corresponds to this, this plus this, what do they call it? A diacritic, that thing, and this thing are now removed or added to, I see, they're right there. My screen looks like a smudge, but it's not, it's just part of the language. So what you see here is this thing has like a little curve right there, and that got added right here. And here got added right here to the top, which bring us to the 4 characters that describe this word. And this is probably how it's actually written. Okay. Rust provides different ways of interpreting the raw string data that computers store so that each program can choose the interpretation it needs, no matter what human language the data is in. A final reason Rust doesn't allow us to index into a string to get a character is that indexing operations are expected to always take constant time, O1. But it isn't possible to guarantee that performance with a string because Rust would have to walk through the contents from the beginning to the index to determine how many valid characters there are. Okay, this one makes sense. So what they're saying here is that when you use indexing, it is implied that you're going straight to that character, straight to that slot, and that is O1 runtime. Going directly there, there's nothing to look at. However, given the way strings are stored, in order to figure out what's there, you have to iterate over all the things before it. So it is not O1 runtime. And that itself is just a misleading concept. Slicing strings. Indexing into a string is often a bad idea because it's not clear what the return type of the string indexing operation should be. A byte value, a character, a grapheme cluster, or a string slice. Therefore, Rust asks you to be more specific if you really need to use indices to create string slices. To be more specific in your indexing and indicate that you want a string slice. Rather than indexing using the square brackets with a single number, you can use the square brackets with a range to create a string slice containing particular bytes. Here, S will be, they have hello, they have that word from before, which we conveniently still have here. And they're saying S is the pointer to the range 0 to 4 bytes. Here S will be the string literal that contains the first 4 bytes of the string. Earlier we mentioned that each of the characters were 2 bytes, which means that S will be that. What would happen if we use this instead? Instead of using the index 4, which we know is a valid stopping point for the encoding of UTF-8 for these characters, and use 1, which is half a character, because these are 2 bytes each. The answer is Rust would panic at runtime in the same way as if an invalid index were accessed in a vector. So this doesn't seem like a good idea to begin with. Yes, you can try to create a slice based off how many bytes that you want, but that seems kind of fickle. I wouldn't even bother using it. You should use ranges to create string slices with caution, because doing so can crash your program. Yep, that makes sense. Next, methods for iterating over strings. Fortunately, you can access elements in a string in other ways. If you need to perform operations on individual Unicode scalar values, the best way to do so is to use the chars method. Calling chars on, they have the Hindi word there, separates out and returns 6 values of type char, and you can iterate over the results to access each element. Understood. So if we did this, I'm just going to copy and paste it because I can't type those characters. And that seems to work, but the indenting was off. So we have 1, 2, 3, 4, 5, 6, and we have the diacritic items here as well. So that's if we want to iterate over the chars, because we did the string.chars. The bytes method returns each raw byte, which might be appropriate for your domain. So there might be times where you want bytes. Let's see how many bytes these have. Bytes. We should probably change that because that's no longer char. C for char, B for bytes. We got all those numbers. But be sure to remember that valid Unicode scalar values may be made up of more than one byte. Getting grapheme clusters from a string is complex, so this functionality is not provided by the standard library. Crates are available on crates.io if this is the functionality you need. So what they're saying here is that they'll give you something to iterate over the chars, which does include these things here, and they give you something to iterate over the bytes. However, if you had to figure out what the words were, like the letters individually, they don't give you that in the standard library. They have crates.io and they just point you here. And they're probably saying other people have done it, and you can just search for something here and find it. So, in other words, rely on the community. Okay, makes sense. Strings are not so simple. To summarize, strings are complicated. Different programming languages make different choices about how to present this complexity to the programmer. Rust has chosen to make the correct handling of string data the default behavior for all Rust programs, which means programmers have to put more thought into handling UTF-8 data up front. This trade-off exposes more of the complexity of strings than is apparent in other programming languages, but it prevents you from having to handle errors involving non-ASCII characters later in your development lifecycle. Let's switch to something a bit less complicated, hash maps. So I'm going to stop the video here, but it looks like the next section is going to be over hash maps. I hope this was entertaining. I hope this was useful. And outside of that, I'm going to take a break. Peace.